Alright, silly people, here's the situation. This is going to be kind of more of a math-proofy problem, so I get to stretch my legs talking about math-proof theory. Um, but the thing that we're trying to prove here, uh, or rather, we're trying to prove the statement that two non-commuting operators cannot have a complete set of common eigenfunctions, which that is a really loaded statement in itself because of how many negatives we had to apply to get to an actual statement there. But I wrote it in terms of math right below it. It says if the commutator of P and Q is not equal to 0, which means they're non-commuting operators, then if F is an eigenfunction of P, then F cannot be an eigenfunction of Q. That's kind of the math version of the statement. That being said, because this statement is so wacky to work with, we're actually going to try to prove the converse instead, and Griffiths even suggests this in the problem statement. So we're going to disprove the converse statement. So that being, we're going to say that if P and Q have common eigenfunctions, so if PF equals PF and the operator Q acting on F is equal to eigenvalue Q acting on F, then the P and Q cannot be 0. I think are, equal 0, I think. So actually we're going to prove this. This is what we're trying to get to. Yeah, okay. So then all we're going to do is actually apply the commutator of P and Q onto F and see what we get. So this will be, by the definition of a commutator, operator P, operator Q times F minus operator Q, operator P times F, which if you just evaluate both of these by their eigenvalue equations, this is little q on F minus Q acting on little pF, which you can of course move the eigenvalues around since they are just constants. So there's that, and then you can act the new operators on them again. So that's Q little p F minus P little q F. And so now that we have everything multiplied by the function at the end, we can cancel out the function on either side. So P with Q, the commutator, is equal to QP minus PQ. So that is actually just 0. So yes. So what we did, we proved that if you have two operators that have a complete state of common eigenfunctions, that those operators have to be commuting operators, which is the same as proving the statement up at the top. So we kind of had to go through a loop to get there, but it's pretty sound mathematically and logically. All right.